Today you will learn what role magnetism plays in the functioning of a DC motor or a DC generator. Now to explain this, I have here examples of different metals. You have here brass, aluminium, copper and iron. And here I have a cylindrical magnet. Now this cylindrical magnet has north pole and south pole. It is cylindrical in shape. So what I will do is, I will pass this magnet over the brass pieces. You will see it does not attract. Again over the aluminium pieces. So also here also it does not attract. Over the copper pieces. But when I bring it over the iron pieces, you will see that they are attracted. Now here you observe a physical phenomenon in which the force of this magnet attracts iron. So here, what is a magnet? A magnet is a ferromagnetic material that attracts iron particles. So apart from iron, it can attract iron, nickel and cobalt. So magnet is a ferromagnetic material which attracts iron, nickel and cobalt. Now here I will place this iron pieces surrounding this magnet. Now when this magnet is at the center and iron pieces surrounding it, it does not attract. But as I bring closer this iron pieces, you will find slowly they will be attracted. So the space surrounding this magnet where its effects are observed is called magnetic field. So when an iron piece is closer within its vicinity, it has the power to attract. Now magnets are broadly classified into permanent magnets and temporary magnets. Now temporary magnets are also called electromagnets. Now in permanent magnets we have four types of shapes: bar magnet, U-shaped magnet, horseshoe magnet and cylindrical magnets. Now electromagnets are produced by passing electric current. So electromagnets are temporary magnets. They act as magnet as long as current is flowing through them. Now here you see a bar magnet. Now bar magnet is rectangular in shape. So one of its end is a north pole and the other end is a south pole. So magnet has two poles, north pole and a south pole. Now here you see there are imaginary lines of force which travel from north pole to south pole outside a bar magnet and from south pole to north pole inside a bar magnet. Now if you observe carefully, these are curved loops. So magnetic lines of force originate at north pole and terminate at south pole. These magnetic lines of force are more crowded at the ends. Now these lines do not intersect or cross each other. So the space surrounding a magnet where its effects are observed is called magnetic field. Now if you observe a U-shaped magnet, the magnetic field will be almost straight line from north pole to south pole. Now these magnetic lines of force are responsible for attracting iron, nickel and cobalt. Now these two magnets are examples of permanent magnets. Now here in both these magnets you cannot increase or decrease the magnetic lines of force. Second thing, you cannot have any other shape other than bar magnet, U-shaped magnet, horseshoe magnet and cylindrical magnets. The third disadvantage is you cannot reverse the pole. So once this end is ascertained to be North Pole, it will always act as North Pole and this pole as South Pole. Now all these disadvantages which we have in permanent magnets can be overcome by preparing electromagnets. Now when electric current passes through a conductor, it produces magnetic field. Now here I have shown a conductor, a wire. Now when current passes through this wire, it produces magnetic field. Now the direction and shape of this magnetic field is different from what you have observed in a bar magnet. Now here, when current flows in this direction, the magnetic field takes the shape of concentric circle. Now here, there will be number of concentric circles at each point in this conductor. So when current flows through this conductor, it produces magnetic field which takes the shape of concentric circles. Now these concentric circles move in certain direction. So to find out that direction, we are making use of right hand thumb rule. Now I will show here how you use this right hand thumb rule. Now here let us assume this is a conductor. Now here there is an arrow shown. So this arrow indicates that the current is flowing in this direction. So what does right hand thumb rule states? Imagine you hold the conductor in your right hand such that the thumb points in the direction of the current flowing through the conductor. So current is flowing in this direction. So thumb is pointing in this direction. Then the curled fingers gives the direction of the magnetic field. Now in this case, the magnetic field will be clockwise. So the curled fingers move in this direction. So the magnetic field produced by the current carrying conductor are clockwise in this direction. Now the same thing you can find out by using Maxwell's corkscrew rule. Now here the current is coming out of the conductor and at this end current is going into the conductor. Now if I turn this side, you will see a current coming out of the conductor is represented by dot mark, whereas current going into the conductor is represented by cross mark. Now these both directions I will indicate here and show you how you can easily find out the direction by using Maxwell corkscrew rule. Now here, this is the cross section of the conductor. When you see the conductor on the sideways, you will see it is round and dot indicates that current is coming out of the conductor and cross mark indicates that the current is going into the conductor. Now magnetic lines around a current carrying conductor are concentric circles. Circles having the same center but different radius. Now when you are using Maxwell's corkscrew rule, imagine you drive the corkscrew in the direction of the current. Now here the current is coming out, so you drive it in this direction. So it is coming out. So what you will find here, this direction, it is anti-clockwise. Now here the current is going into the conductor. So you assume that you are moving the corkscrew in the direction of current. So when it is moving in the direction of current, it will be clockwise. Now in the earlier demonstration, you have observed that magnet has power to attract iron, nickel and cobalt. That means it has magnitude, and here you see it has direction. So magnetic field has magnitude as well as direction. So it is a vector quantity. Now we will use this notation of current going into the conductor and current coming out of the conductor in learning the principle of a DC motor. Here you see a straight conductor and current flows in this direction, in the direction of the arrow shown in the straight conductor. So at this point or at any point in this conductor, when current flows through the conductor, magnetic field will be produced. Now to increase the strength of the magnetic field of this conductor, what we do is we turn this straight conductor into loops. So I have turned the straight conductor into loops. Now here at each point magnetic field is produced. Shape of this magnetic field are concentric circles. So what happens? 2-3 loops of magnetic field join together to form a bigger loop. So the strength of the magnetic field is increased by turning the straight conductor into loops. So this is a coil. Now this type of coils are used in windings of a motor. So when current flows through this coil, it produces magnetic field. Here you see the positive terminal of the supply and negative terminal. So when current flows through this coil, it produces magnetic field. If we place a soft iron core inside this coil, when current flows through this coil, the soft iron core acts as a magnet. That means when a coil is wound on a soft iron core and current is passed through the coil, the soft iron core acts as a magnet. Now here I have placed a soft iron piece inside this coil. So when I pass electric current through this coil, the soft iron piece acts or behaves as a magnet. So this becomes north pole and this becomes south pole. Now here I have kept a bar magnet picture ready. Now if you see here, the magnetic field is same. That means imaginary lines of force travel from north pole to south pole and they are closed circular loops. If you look here also and here also, the imaginary lines are same. Now what is the difference? In case of a permanent magnet, these poles cannot be changed. But if you reverse the current flowing in this coil, then this north pole can be changed to south pole and this will act as north pole. So magnetic polarities of an electromagnet can be reversed by changing the direction of current flowing through the coil. Now second advantage of an electromagnet. Now here this magnetic field is constant. You cannot increase or decrease the strength of the magnetic field. Whereas here, by changing the strength of the current flowing through the coil, you can increase or decrease the magnetic field. Now, here, as you increase the number of turns of this coil, the magnetic field becomes stronger. That means the magnetic field is directly proportional to the number of turns to this coil. So you increase the number of turns of the conductor, the magnetic field will increase or will become stronger.